you have wide enough columns and so forth to be fairly stable, using just inertia, you can get your temple to stand up, but there's no real trick to knock temples down, and that's what they did in the past because of the instability of the 90-degree angle. 60-degree angle is completely stable, and 90-degree is completely unstable. Two coming together, and there was one went out this way, and then one went into us. There are four factors. I began to think way back in those Navy days about, I like the idea of vectors, and I like the ideas of models and their interactions, and you could seem to prove quite a lot, but I wondered what really was there a possibility of some kind of a minimum set of force patterns that are operating in the whole universe, not just in a little local system such as a diagram regarding two boats or two locomotives or two billiard balls. I said, for instance, here I am in the universe, how many forces are really operating on me? I suddenly find that I can move around all right, but all I can do is to move in a plane. I can go around and around in circles. It does tend to make those figure eights and so forth. Like a music string, it could go around in circles or figure eights or in something in a plane. Then I'm going to give myself a third restraint. And make that model. Now I have a saddle for my foot, and I have three restraints. And this time I can still move, but now I'm only moving a line. This is very much like a drumhead. The previous one was like a violin string. This is like a drumhead. And I see that I can go really quite positive. I can go over and make a positive tetrahedron and go over and make a negative tetrahedron. And I'm moving back and forth in common altitude of these two tetrahedron. Now, supposing I get pulled into one tetrahedron or the other, and so that's the positive and the negative tetrahedron. Here we have four restraints. And with the four restraints, for the first time, I seem to be immobilized. And so I became convinced that what we call fixed in universe is the product of four restraints, and that it was the equilibrium of the drumhead taking either a positive tetrahedron or a negative tetrahedron condition. That's all it is. But I used to think that I could make this very, very stable. If you don't mind holding the bottom one down, but at height where somebody can see it, like that. And I used to think this is very stable. All I had to do was to make it out of very strong wires. But I discovered even how strong the wires were, I could still do this. I can rotate it right in. The center of gravity stays right where it was. But by rotating, I pull a little against the gravitational pulls. The four gravitational pulls have to yield to me a little, but yield they will. Therefore, I began to discover that the only way I could make it completely stable, so there'd be no local rotations. I have two triangles. And we take the two triangles and we add one triangle to the other and do it this way. Break open this vertex here. So I take two triangles, add them together, and I get four triangles. It's interesting that 1 plus 1 equals 4, because there are four triangles. This is really a very definite synergetic demonstration. You see the three vertexes in the South Pole and the three vertexes in the North Pole, and the 6 vertexes around the equator. And how completely unstable this thing is, because it is vector equilibrium. I've taken out the 12 radials. I wanted to see what would happen if the external system, say, took ascendancy over the internal system, going from the vector equilibrium, so that I've now weakened the interior, and the system is able to collapse. It can't explode, it can't get any bigger than this, but it can get smaller because the interior restraints have been eliminated. I'm going to drop this top triangle in my hands towards the triangle on the stool. The triangle on the stool the top vertex of this triangle up in my hands is directly over the mid-edge of the triangle on the stool. I'm going to lower this top triangle towards the triangle on the stool. I'm not allowed to twist it or anything like that. I'm simply allowed to let gravity take over because I'm holding it up in the air, and I'm going to just let it down slowly. Letting down, letting down. Could you help me hold the triangle on the stool? Get around the back side so you won't get in the picture. Now I lower. Can you do it with one hand? Can you do it by holding this just in front of the corner on the outside so you won't have your hand inside? That's the point. Now I lower this top. The bottom triangle must not twist, and the top one must not twist. So it goes to the vector equilibrium. Now it becomes the octahedron. And you may best stand by me here a minute, because I hold it steady if you can. And I go down and become the octahedron, then pick it up. Notice it goes by the point of equilibrium. I just lift this top triangle up and down. I do not twist at all. It goes by a dead center and becomes another octahedron. One octahedron, two octahedrons. These are entirely different octahedra. What is happening is that the whole system contracts symmetrically. All 12 vertexes move towards common center at common rate. At this point right here, for instance, and as this collapses, the equator is now starting around this way, and this will rotate like that, and this plunges through here. This becomes then the tetrahedron. I'll do that down to the floor where the thing will stick a little better, and you'll see what happened. We have the system being rotating. It's rotating like that, and there's a great momentum of the rotation. Therefore, the head, this end, gets rotated more still, and it plunges down, torque, and plunges clear through, and folds up and becomes the tetrahedron. Then the tetrahedron can turn itself in. Maybe that's an oscillation comes to an energy end like this, locks up and bounces back because it gets in that critical proximity business, not to an absolute point. And then it bounces the other way. So this will plunge inside out on itself, oscillate back and forth. Very much the way the double stars do just exactly the same thing. Now, that's another case of vector equilibrium. There's the four great circles of vector equilibrium.
Sorry, could we do that again?
This way, I've been traveling around with this for many, many years. I often throw it out in the audience, and if there's a light switch hanging out in there, you could maybe catch on it. I'm sorry, it's broken. No? Broke that moment. A little bit. And very, very evident to you in this case. Much. There's your vector equilibrium again. Now, I'll give you one more on the vector equilibrium. The vector equilibrium. This is something that would be the result of a spin. This is very powerful. I've discovered that I can, if I spin it in my hand like this, I try and press down on it, it just pumps out against me. Just the rotation itself pumps against my hand very, very vigorously. It's quite an experience to do that with your hand. So now we get out of the vector equilibrium condition, and here is the vector equilibrium itself. Here we have open squares, and here we have closed squares. And we take the closed squares and we rotate this one, and she opens up. Now, when the system opens up, as it does here, just is quite interesting. Just as the chemists have decided that their relationships do the compounding of atoms, that is, the 8 little wheels are in a position where, if I rotate this now, you see I can get it where these little papers point each other. Each wheel has 3 white papers on it. Each wheel touches 3 other wheels. If I made a line between the points of contact, I would simply have the 8 triangles that I had in that little pumping the vector equilibrium, which was this unit over here. To rotate like a gear on the triangular point, and then they can come until the triangle sides are touching one another. In this case, however, the triangles are fat because they are circles and they're just triangular contact. So when I rotate them, they can't collapse the way they did here, which is. Can you pick this up neatly, everybody? You all see it? Right. Now then, with all 8 wheels rotating, we have something very interesting. If they were odd numbers of wheels in a system, the system blocks as here's 1, 2, and 3 wheels. These are gears. If this gear is trying to go this way, then this one here will have to accommodate by going that way too. The piece goes that way. Which would mean then that this one here is going like that. Which would mean that this one here has to go this way to accommodate it. It would be going like this here. But this one here is going this way, so this one's trying to go that, and this one's trying to go that, and the gears strip. So that they block, they either strip or block. If there are 4, however, then the even number, this one goes like that, and this one goes like that, which means that this one's going like this here, which means this one's going like this here, which means this one's going like this here, this one's going like this here, which means this one's going like this here, which means this one's going like this here, which is just what that arrow was doing. 4 will do. There are, then, in this train of gears, while each gear touches 3 other gears, so it can't move. I'm just holding it. We know that all these wheels are reciprocal, don't we? There can't be anything else from now on. So I'm going to turn them, and you find that the 3 little wheels at the bottom are rolling around on the bottom one, and that forces the ones above them to roll. And then look at the top wheel. Standing still. Can you see the papers on it? Standing still. The fact is, it really isn't standing still. I'm immobilizing the bottom wheel. There's a train of gears, and they're all reciprocating, exactly as they are now. But if I immobilize one in respect to you and I, it looks like the top one simply stays in line, arranged with it as. Then I set this top wheel on top of here and hold on the bottom and rotate the system, and the little top wheel stands still. We put something on there so you can see it. It's aiming right at you. Yesterday I established the idea of a geometry in which the lines would consist of vectors. I said that because it was consistent with our definition of universe, that we were dealing in the universe was the aggregate of all men's consciously apprehended and communicated experiences, and in my kind of investigation, I'm not allowed to deal in any patterns that are not of experience. And the patterns of experience are brought into linear consideration by our realization that vectors are just such linear actions, linear relationships. And you yourself can demonstrate this to yourself by, say, taking a ball and massaging a ball which you've been able to throw, which has a certain amount of windage, and massaging it into a sphere that has very much less frontal area, therefore it moves with less friction, and it develops a momentum, a directional momentum. It's very easy to throw the sphere accurately. And you begin to discover that battleships or railroad trains which are running into each other as vectorial problems could literally be massaged into continuous ion devices in which the ion spheres or vectors in common association, an octahedron common association around one point, the circumferential chords were exactly equal in length magnitude to the totality of all the radii. Therefore, the tendencies of the system to explode or to contract were beautifully met. Now, that arrangement has a lot of significance because now the spherical four great circles of the vector equilibrium. Now, if I pull on any one of these arcs, they become a chord again. If somebody would stand up with me and help me pull on each of these vertexes, we'd find the whole thing becomes the chorded vector equilibrium. But when it is so, the radius is, when it is chorded, if I pull on this a little, the radius increases to accommodate it. If I let the radius contracts, then it becomes spherical. We discover that the sphere represents a vector equilibrium where its chords have become convex outwardly of the system by virtue of a first degree of contraction of the vector equilibrium. The radius has been contracted. Spheres represent a first degree of contraction of the vector equilibrium. And we'll run into that time and again in our modeling until we begin to be quite confident that's exactly what is going on. I could take the vector equilibrium itself as the model we've been pumping with here, and here it is in the chorded condition. And taking the chorded condition, I can then deliberately bend each one of these chords outwardly, and that means that the radius will contract. And you see, there's something else I could do. I could bend all the arcs inwardly, and that would give me a concave vector equilibrium. So I'll call a sphere a convex vector equilibrium, and then there's something I call a concave vector equilibrium, and we will discover it later on this afternoon several times. And we begin to get familiar with these two ways, and these being ways in which the empirical universe goes from the vector equilibrium, which we've discovered nature tends to abhor, and insists on taking a positive or a negative set of one kind or another. And one of the positive or negative sets it could take would be for the vector equilibrium to have its chords go outwardly and become convex, or go inwardly and become concave. I will throw this up just once more and like to show how it does fold up into a tight little bundle, and then here's how it becomes a sphere again by itself. One reason it becomes a sphere is because it has the triangles, and triangles insist on, they are inviolate structurally. The quadrangles can be changed. They have no particular structural, they have no structural stability whatsoever. And the tetrahedra, which the little pink edges that you'll see in here represent the common edge between adjacent tetrahedron. Here's a tetrahedron here, and there's another tetrahedron here with a pink edge between the two. And when we do that, we get octahedronal interstices as a result. But we cannot put tetrahedra face to face and fill all space. We put any two tetrahedra face to face, and there are other things that can occur. But if I want to keep on with the continuity of this tetrahedra face to face instead of, and it does wind around and around. It becomes a helix, and this particular helix is quite exciting. And then we find that when we've added tetrahedra to tetrahedra, every time we get to 10 tetrahedrons, we get back to the point where we started before. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At this point, I'm at the end of the first tetrahedron. We can separate this off. Here we have 10, and I must have made a little error in my counting, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have one too many. And you will find that the top tetrahedron is in the same attitude as the bottom tetrahedron. as every 10, it makes a complete cycle. And that became very exciting to us because we discovered that such a tetrahedral column making a helix does so in a manner that comes around and makes a complete cycle every 10. Now that happened to be identifiable with something which I might as well introduce right now, what's called DNA, the deoxyribonucleic acids, DNA. And DNA consists of 4 primary chemical compounds we just call them for the moment TAGC. They are thiamine and adenine, the G and C, cytosine and guanine. They wed one with the other. And on the other hand, we find that when we wed them together, they bring about, for instance, the point right here you're looking at towards you where there are 5 tetrahedra around one common edge. The edge which I'm pointing at right here towards you is the edge of the common 5 tetrahedra around one edge, one axis. Now, the edges of tetrahedra, we know what their angles add up to. They are 70 degrees and 32 minutes. And if I try to put 5 discrete tetrahedra around one common edge, 70 degrees and 32 minutes times 5, would you just multiply that out for me? That comes out, would you just multiply 70 degrees and 35 minutes, which is approximately the spring in the system. Therefore, when I let go here, it tries to unzip itself because it does have the spring in it. In the characteristic of DNA, they find that all the patterns of any given species are transmitted by dichotomy they have a double helix such as I have here, 2 of them pulling side by side, fitting to one another, in which at a certain point that one will break off from the other and the child will carry on the pattern of the parent. And this is the way species designs are carried on by nature. And so we find here in our energetic geometry, just poking along with our tetrahedra and finding out everything we can from tetrahedra, which is the first geometry which we've discovered, and finding out what it does, that we followed then on in face-to-face, or triple, when you use face-to-face, we call that triple bonding. In the organic chemistry, vertex to vertex is called single bonding. We would call it universal joint in mechanics. Basic triangulation. And that gives the most stable and most powerful of the bonds, the triple bonds. There's one more bond known to the chemistry, the organic chemistry, and that is when we have all 4 vertexes. If I could open this one up and insert this one here, so all 4 vertexes are congruent. That is called quadrivalent, or 4 bonds, and carbon, which is really very soft, and as you know it in charcoal and so forth, can become extremely compact when it is quadrivalent, and we have it as diamonds. When it is joined together, this enormous. Very interesting. I can make 4 different size balls. It will still give me a tetrahedron very perfectly well, because any 2 balls, no matter what their size, can touch each other, can't they? And I can always nest a 3rd ball in the crotch between the point of contact, no matter what the size of the 3. And once 3 of them together, they form a little nest like this, and a 4th ball can always be nested in it, no matter what its size. The tetrahedron arrangement permits an enormous variety of sizes. The only one thing could happen is that the 4th ball could be too small and fall through the hole in between there and not stick. And there is then a limit of the nestability, as the 4th ball must be of a size that does not fall through the hole. As the only limit. But the interesting thing, there is a limit. And the same kind of limit begins to show up square, as we're familiar with it, and we make modular subdivisions of its edges, and we make these 90-degree crossings, and we say 1, 2 times 1, 2, 2 times 2 equal 4. And we finally have 1, 2, 3, 4 squares. And there are diagonal ways of doing this with points, but the square area is what we really care about, so I'm doing it simply in areas. So we say 1, 2, 3 times 1, 2, 3 equals 9. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. That is our way of handling 2 times 2, or second powering, or 3 times 3, or 4 times 4, which we call powering. And we've always called it squaring. I find even the most advanced physicists, Whittaker himself, would be talking about squaring and cubing. It's surprising to me that how we really froze onto that. And Whittaker himself is examining the relationships of arithmetic and geometry. And this is arithmetic and geometry, the integration. Apparently man never thought of there being any other way of doing this. So I found it very surprising when I first discovered that we could say, I can take the triangle, and I'm going to take modular subdivision 2, and interconnect again. These points is the 1, 2, 3, 4, which would be 2 times 2 equals 4. And that's applied it for the so 1, 2, 3 times 1, 2, 3 are the 2 edges. 2 to 3 equals 9, and then 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then try it for the module 4. So 4 times 4 is 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Quite clearly you can say triangling instead of squaring in terms of the frequency of modular subdivisions of edges of the system. And if you can, quite clearly a square is 2 triangles. And so to say triangling would be twice as efficient. We're not wasting a lot of space in order to identify our arithmetical behavior, which shows this kind of multiplication result. So the next thing we will do is we know how then we'll get the 8 cubes around the 1 point, which had a module of an edge of 2. So 2 times 2 times 2 times 2, or 2 to the 3rd power, gave us 8. But I'm going to try that same thing in triangles. Another triangle here of 3 base. And one of one little triangle over here. One there. Now, we have at our present a tetrahedron, so I'm going to draw a little tetrahedron on each of those triangular faces. I put one on here, I put one here, but we learned yesterday I can't put one in here because it won't fill all space. There's an octahedron that comes in there. Now I'm going to put another tetrahedron here, Always doing every other triangle becomes tetrahedron in the system, but starting with the corners. Francis, be sure to catch these. Now, I'm going to, at the top of each of these tetrahedron, I'm going to interconnect them, and this gives me the octahedron inside there, and another octahedron shows up here. Another octahedron shows up here. Another octahedron shows up here. Octahedron has orange top triangle and then blue lower slanting up and downward edges and a white base. Now, in this accounting, my tetrahedron has a volume of 1. In this case, here I have 1 tetrahedron,